Anyway, unsure if that's the case for me. But, and a lot of lectures were old, so I think this is one of the new ones. 50 more seconds. I guess I don't need to repeat the announcements. If you want feedback, send us your proposals sometime on or before the spring break. Either way is fine. I have one unresponded email. Unfortunately, I don't have time to meet in person. If the person is listening, I'll respond by email. This is about, I think, some chemistry code as a project. And good luck with the UPC homework. So let us get started. This is one of the new lectures. I think the sorting and searching was kind of new, somewhat old. This one is almost from scratch. And we're gonna, I'm gonna do the first, I'm not gonna call it half, about 70% of the lectures. And Aditya will take over and finish the lecture with another method that is very well suited for parallel computing. Or it wasn't, he made it do so. So what is machine learning? I couldn't find a good definition. But here's an indirect definition. What machine learning tries to answer. What's the question? So the question is, how can we build computer systems that automatically improve with experience? And what are the fundamental laws that govern all learning processes? Okay, so there's a systems component in this definition, and there's a theory component. That's why you're going to see lots of theory conferences and journals about what are the limits of learning. And you're going to see a lot of systems-oriented conferences and journals that build machine learning systems, right? So that's very natural because the research area touches both. Here's a very coarse-grained classification of, I would say, machine learning tasks or classes. In the top level, there's classes. There's supervised learning where you're given a bunch of labels or values, so you know something, and you want to be able to predict things that you don't know of. The reason is supervised because you have training data. And there's two classes of that. In broad terms, really, it's regression and classifications are only different based on whether their response values are classes like 0, 1s, or just numerical values, where it becomes regression. Unsupervised learning, on the other hand, doesn't have training data, so you try to make sense of the data from scratch. And clustering and dimensionality reduction are good examples. And we're going to see one dimensionality reduction algorithm today. And then it comes to things in the middle. So semi-supervised learning is really when you have your data half-labeled. So you don't know all the training data you need, but you have some training data with lots of missing data. So you're trying to fill in and also train at the same time. And then reinforcement learning is when you get actually feedback from either a user or some other mechanism. You can continuously improve your learning process by essentially reinforcing good behavior. And that can happen by when you're playing for some sort of like game, like chess or Go, where you do something better, and you learn that, wow, what I just did increased my score or winning probability, so I should keep doing this more. Of course, it's easier said than done. A couple of sources of confusion, at least for me. Maybe you have the same confusion process when you start looking at this if you're not a researcher. Method versus task, very commonly confused. So what is it that I'm trying to achieve? I want to reduce my dimensionality of the data set. I think my data set has way too many features. Like there's a million features in my data set, but I know that only probably 5, 6 of them are going to capture most of the important data. So I want to reduce all that feature set to something manageable, because high dimensions are usually harder to train, harder to compute on. There's lots of redundancy comes into play. There's statistical issues and computational issues when you have high dimensional data. But so the task is dimensional reduction. One method to do that is principal component analysis, which is essentially singular value decomposition in a different interpretation. And another example is we want to do some supervised learning, like classification or regression. Support vector machine is a method to do that. And we're going to see support vector machines as well. The second confusion comes from optimization technique versus the learning method. So we talked about the methods. So support vector machines is a method or tool. And neural networks is another tool. So how do you train these things? Because the optimization method is usually how do you train them. The most popular way to train support vector machines is, for example, an algorithm called sequential minimal optimization. And we're going to see this and other methods as well today. And probably the most popular technique to train neural networks is stochastic gradient descent. And don't pick me on that word. We'll get to that as well. So is that clear? Because it's going to make life much easier whenever you try to understand these concepts. So let's get to our famous matrix of motifs or dwarfs versus, I don't even know what the y-axis should be called, applications, problem domains, things like that. Right? So I don't think they labeled it very well ever. So as you can see, I highlighted the machine learning column here. And what does it touch? It touches graph algorithms. You've seen the previous lectures. And I tried to give a couple of examples where graph algorithms are useful in machine learning tasks, such as dimensionality reduction. There's dense linear algebra and sparse linear algebra. They're all very red, meaning that heavily relies on. And in addition to that, there's graphical models, backtracking, and dynamic programming. These two actually are awfully close to each other in some sense. It's like dynamic programming is backtracking without backtracking. It's like keeping track of the thing on the table, right? So unsurprisingly, we're going to see a lot of linear algebra today as well. But I'm not going to repeat all the things that we've seen. So I'm just going to defer to what we have already seen whenever possible. And here's why we're going to see a lot of linear algebra. Lots of machine learning actually relies on linear algebra, right? So here's a little dependency graph. It doesn't cover all the machine learning tasks, but it covers a good subset that I'm familiar enough to actually claim this dependency is exact. So you see the bunch of classification tools, logistic regression, support vector machines, and similarly another set of supervised learning. That's why they're green. And what linear algebra kernels they depend on. And dimensionality reduction tasks, clustering tasks, and partial correlation estimation, also called the sparse inverse covariance matrix estimation. And they all depend on a bunch of BLAS operations, either sparse BLAS or dense BLAS, and so on. So that's basically the general idea. But that's not the only way to parallelize a machine learning task. So if you think that you can just say, well, it looks like these guys are calling these linear algebra operations one after the other, so why don't I just parallelize these guys, and probably I'll get the best performance? Well, not always. It depends on the application. Sometimes if the outer loop or outer iteration is taking too much time, meaning that there is a long critical path, no matter how well you parallelize these little pieces, you're not going to get the best performance. And sometimes you don't need to be that exact. And we'll see some examples where you can kind of divide and conquer approximately, because most machine learning tasks, by definition, are approximating something that you don't even know. So you can cut a few corners, and you'll be surprised sometimes it works just as good. So the implicit parallelization is the first approach. I parallelize the matrix linear algebra operations that machine learning tasks depend on, right? Or in general, this is just one example, of course. The general approach is keep the machine learning algorithm as is and parallelize individual function calls in there, right? So that's one way. And an explicit parallelization, and this categorization is, of course, a little fuzzy sometimes, is you want to modify the whole algorithm itself so it looks like something different, but it computes the same objective function at the end of the day. And the communication avoiding SVM and communication avoiding block coordinate descent, we'll see, are probably examples of those. And so here's the lecture outline. Really, after this introduction, we'll dive into a couple specific cases. We'll see training support vector machines, training neural networks, finding a non-negative matrix factorization, and Aditya will talk about block coordinate descent. Any questions about the introduction? So one thing that's really hard is how long this lecture is going to take, because it's not has been attempted, so we'll see. So what's a support vector machine? Really, it's about you have, think about this classification task. You have black dots and white dots, like, or empty dots. You want to separate them. And support vector machine, the one idea is to find a plane. If you have a two-dimensional data, you find a line. If you have a d+1 dimensional data, you find a dimension d plane somehow. Well, but I don't want to find any plane that separates this data. I want to find the best plane I can find to avoid overfitting. And so what support vector machines really formalize this idea. It says, find a plane such that the gap, the margins between the closest points are maximized. So it tries to maximize this margin. It's here b over norm of w, but really it's scale invariant, so I just wrote 1 over w. So that's what it does. And if you look at this problem, it's a giant quadratic constraint optimization problem. You can try to solve this in a off-the-shelf method. It's going to be very expensive. It's going to take a lot of time. So people have developed specialized methods to solve this problem, as opposed to using quadratic. The reason it's called QP, you probably know this. It's called quadratic programming. Somehow the OR community called all these things programming. It's funny. Specialized algorithms we'll see is the most commonly used is probably sequential minimal optimization. What it does is decomposes this giant QP problem into smaller QP problems, and it solves them one after the other. And in fact, the name sequential minimal optimization is really self-descriptive. It actually doesn't solve its smaller problems, finds the minimal such problem it can solve, and does it one after the other. Well, of course, you can ask me this. One natural question to look at this data is, does my data look like this in practice? I mean, if my data really looked like this, I would just use something like perceptron, right? Like the dumbest algorithm can separate these things. The trouble here is many of my data sets are not linearly separable directly. So you're going to see a lot when people say support vector machines are examples of kernel machines. So what is a kernel? So usually my input will look not linearly separable, but somewhat separable, right? There is a way to do it. So what a kernel does, and there'll be another example of this, is it maps to this input space to another space where things are linearly separable. And this is a toy example. I'll show you a real example. And I think the next or two after slides. So essentially, all the points are transformed by this phi function somehow. Well, what's the downside? Because the issue is usually you can't find a transformation within the same dimensional plane. You have to map this to a higher dimension. And so your computational problem becomes more challenging. And worse, if you went through this whole data and transformed it, it might be more expensive than even training them. So what can I do? Well, there's a little trick that's called the kernel trick. And we'll see what it means in the next slide. You don't transform your whole data. You just do computations as if it's transformed. It actually has been used in a lot of other fields, like only transform as you need it in the operations that while you're doing on the fly, simply. So here's a more concrete example from, surprisingly, still one of the best books in the field by Russell and Norwick, the artificial intelligence book. That's probably, how many? It's a decade and a half old, even the second edition. But hey, here's a real example from there. This is your data points. Your black points are inside a circle, so it's not linearly separable. And I find a mapping. The mapping really looks like this. It takes any 2 points and maps them into a 3-dimensional space with this function. And boom, there's actually a plane that linearly separates those in the 3 dimensions. OK, but I don't want to map every single one of my points into 3 dimensions. What do? I define a kernel function. where the trick, it needs to do one thing. The inner product of the transform space, like take one transform point and compute the dot product with another transform point, should be equal to computing the dot products and then doing the kernel function. Okay? So instead of transforming them, I will just be doing the dot product and applying the kernel function. We'll get the same result. So whenever I do dot product, I'm just doing this on the fly. And if you do a little bit of algebra, this is true. You'll see, and you'll now figure out what function will work in your space. But it's doable. So that's what it means. And it's only to serve you whenever we say kernel, this is what it means. It's not going to change the algorithms we're going to develop. It might make it a little nasty on the details, but that's all. So here's a little worded, highly worded slide. Apologies. So your input is usually n by d, right? And n is the number of samples or examples. And d is the number of features or dimensions of the data. So you don't compute, this is what I exactly explained. You don't compute the kernel, because it's giant, it's more expensive, and so on. So you use sequential minimal optimization. These are all the things that I've been saying in pictures, in writing. But there are two things that's new in the slide. One, what does SMO does? It really only touches 2 rows of the kernel matrix. And again, I'm not forming the kernel matrix, the hypothetical kernel matrix at the time. And the main driver of this algorithm is a matrix times a sparse vector. And if your matrix, if your input is sparse, it's usually sparse matrix times sparse vectors. So that's where the dependency comes. And you can use the same algorithm we've used for the breadth first search to parallelize this. But it's not going to be very efficient that way, because your vector is only 2 non-zeros. So it's pretty too sparse to probably take advantage of lots of parallel cores. So there is a more formal definition. This is what sequential minimal optimization really does. Don't worry about the long formula. It's a quadratic optimization problem subject to some constraint. Only look at the constraint, which is the interesting part, the inequality constraint. What does it say? This goes to duality and all that, but short answer is all the support vectors has multipliers. These are called Lagrange multipliers. So if depending on that value, you can tell whether that point lies on the boundary, meaning that it's one of the support vectors or not, right? So not all points are active, only the points on that support. I guess that's what I forgot to mention. Whoops. Only the points on these support vectors are the active guys, okay? These guys have meaningful Lagrange multipliers. Everything else is probably 0. So one interpretation of Lagrange multiplier, from what I remember, is it tells you how much your solution will change if you perturb that value a little bit. So if it's 0, it means it's not an active constraint, right? Good. So, well, so how can I change these, perturb these Lagrange multipliers? Well, I can't just change one of them at a time, because the constraint says the sum of multipliers times these y1 values should be equal to 0. If I perturb one of them, and if my constraint was valid, now it will definitely be invalid, right? I will be violating my constraint because this is an equality constraint. So the minimal thing I can do is to change 2 of them at a time. Pick 2 alpha I and alpha j, and then jointly change their values so that this constraint is still satisfied. This is one way of doing it. There are algorithms that will violate the constraints, that they're actually going to be not feasible during the optimization and only become feasible towards the end. But this algorithm will keep this constraint feasible at all times. So it just picks 2 multipliers and modify them. And here's the algorithm in its original papers. And what I just said in words is in writing here. Select some pair of alpha I, alpha j. And there's a heuristic I have to choose them. And then modify them. Yes, question?
So just a minor point. Why is it called the inequality constraint if it's equalities?
Where's the inequality? Oh, it should say equality. Okay. Sorry. It's just, I'm glad I didn't put them yet. So I'll put them online, and they'll be fixed. The problem with this is the number of iterations you need to do is on the order of the number of samples. In fact, there's a constant. There's a large constant there, too. So they're proportional. Well, that's a little problematic. I might have a loss of samples. The reason this is really I'm just treating 2 samples at a time. So it's going to take a long time. And for parallel computing, what this means is you have a giant critical path. Right? So this is not good. Here's the first approach to solve this problem. Partition the data, the samples, to P processors. And then find the support vectors in that partitioned data. Every processor finds its support vectors. And now passes these support vectors in a tournament tree-like fashion. Remember the LU factorization tournament tree idea? So the first 2 processors will jointly solve the next layer problem together. And 2 and 3, usually this means just one processor. 3 will do take over from 4. And 5 will take over from 6, and so on. Now they will find the best support vectors on that combined data set and pass it to the next layer. And this will iterate. Okay? So what am I passing at every layer? This is basically logarithmic. Log p is the number of layers in this process. And the point here is I'm only passing support vectors and their Lagrange multipliers. Okay? So, and I don't actually need to pass these Lagrange multipliers, but that allows me to do a warm start on the solution. It converges faster. It's a better initialization. So that was the first idea. That's, as you can see from the date, that's more than a decade old. And a decade later, somebody came up with a similar idea, which awfully looks the same, except that now instead of passing just the support vectors, the data is also, all the data is available here, meaning that support vector 1, 0 has all the data that support vector 0, 0, and 0, 1 had. So it kind of resolves the problem. But the amount of data that's communicated at every layer increases. And if you look at the results, this one actually has better accuracy but significantly slower than the Cascade SVM. So there are 2 points in this paper. Is this cited here? It will be cited towards the end. So the divide and conquer SVM essentially relies on 2 ideas. One of them is the support vectors of the subproblems are close to the support vectors of the global problem. Under some conditions, you have to look at what it is. And the second one is the partitioning algorithm that partitions this training data set to pieces, the kernel k-means algorithm, is actually minimizing the solution of this really subproblems and the global solution. So essentially, the whole algorithm relies on this idea. Here's the difference between the previous algorithm. The initialization of the previous algorithm actually didn't use any kernel k-means. So there's less theoretical guarantees about the accuracy. And in fact, practically, it's worse. But it's cheaper. Well, it's natural to combine these 2, right? It looks like one of them is computationally cheaper, and the other one is giving me better accuracy. So the first attempt is something called a divide and conquer filter algorithm. So in order to not make the algorithm expensive, I use the same idea with Cascade SVM. So I'm only passing support vectors. But in order to be able to prove some accuracy and get better accuracy, I'm using the kernel k-means to divide the data set. So it looks like we're done, except we're not. So here's what's happening. I have P processors busy. I have P minus P2 processors busy. I have P minus 4 processors busy. Naturally, I'm wasting lots of processors as layers increase. And here's actual data to justify this. The first layer takes 6 seconds. And first it goes down, because I'm not passing all the data, right? I'm just passing support vectors. But then as I go lower, because there's only one processor that's busy, towards the end of this tree, the time it takes to solve the smaller problems down there is actually taking longer, because I don't have the computational power anymore. I'm wasting all my processors. Well, how can I solve this problem? Is the next attempt. Cluster partition SVM. Really, you do, again, k-means to partition the data. So you use the good idea for accuracy. But instead of doing a tree reduction, everyone trains their models, and some global merging happens here. Okay, good. Well, why does this even work, right? It turns out for various kernels, you can make this work. The idea is, think about the Gaussian kernel, where if you look at the Gaussian kernel's definition, you'll see that only the support vectors that are close to the sample itself can affect the classification. So that's essentially the same objective function k-means is using to partition the data. So the things that are not in your partition are likely not to affect your support vectors themselves. So that's what the assumption is. And it seems to work in practice. And but there is a little bit of an issue again. So what's the last issue? The k-means has no balance constraint, right? K-means can find very unbalanced partitions. Even though I'm keeping all the machines busy, the time it takes per machine is highly variable. You see less than 1 second and up to 6.5 seconds. So, well, it looks like instead of using k-means, I'm going to use a more balanced clustering, balanced k-means. It's not exactly replacing k-means, because I still need the k-means properties for accuracy, but it's replacing it with something more balanced like a k-means. And at the end of the day, now I'm keeping my processes relatively load balanced. It's not perfect, but it's good. There's still some research that can be done here. This is only 8 processes. Nobody knows how this is gonna perform in thousands of them. But accuracy-wise, you're not losing too much. So the first algorithm is a distributed implementation of sequential minimal optimization, the golden standard so-called algorithm. And the accuracy we get is 98.7. And Cascade was really bad, but fast, accuracy-wise. And as the so-called communication avoiding SVM, the latest algorithm I described, is awfully close in terms of accuracy, but about 4 times faster. Okay, so question?
Do you do the k-means on one machine, or do you do the operation across machines?
You would ideally do k-machine in parallel, but in this case, it's so much cheaper that it's not, I think. I mean, parallelization of k-means is a topic I wanted to talk today, but I didn't, because the naive k-means is too easy to parallelize. The k-means with sophisticated data structures like KD trees are very complex to parallelize. So neither one of them made sense to have a subject. Either it was one slide or a whole lecture. So, but the whole complex one, so basically since it's hard to implement all the optimizations of KD trees in distributed memory, a naive parallel implementation is not significantly faster than an optimized serial one. So then you have to put a lot of work on getting it. But the idea is there. You're going to learn in the hierarchical methods lecture, right? So the KD trees, you can think of them as multi-pole methods that we'll see in April once you come back. And lots of citations. You can even find the code, and these slides will be there. Thanks to Yang for giving me these set of slides. The hot topic of the decade, no, is it 5 years? I don't know, neural networks. I don't want to call it deep learning because it's the same. Doesn't matter if it's deep too much in terms of what we're going to talk. For them, it matters. So training. What is training a neural network? Right? So a neural network is really, this is the most shallow network I could find. There's only one hidden layer. Here's a bunch of inputs, and it's providing an output. You can think of inputs as your samples, and output is some function you're trying to estimate, predict. And there's one layer. So what does this allow? It allows me to compose functions. Each layer you can think of as a function application. So you, instead of trying to find kernels and mappings, what you're seeing is f of 1, of f of 2, of f of 3. No matter how many layers you add, you're adding another function. So that makes it arbitrarily complex, so you can model pretty much anything. In fact, if you look at practical results, these guys can learn random points. There is no dimension in a random point. You have to memorize every point, and they can pretty easily do it. Of course, it doesn't mean anything. Your generalization error will still be 50% because random point, there's no correlation. But that's OK. So these are very powerful, guys. Training is really, how can I adjust the weights on these connections? There is a bias component too, but I don't want to confuse it. Let's think about it, just weights. Okay, so I need a procedure that changes these weights in my neural network so that I minimize my error. It's also called loss or whatnot. Again, every book will have a different name for this. Here is one algorithm. It's called gradient descent, also called steepened descent. Again, these names are important because you'll see a whole different line of research that's never cited because the name doesn't match the Google Scholar. Optimization people used to call it steepened descent. So what are you doing here? At every iteration, you have a bunch of W's you use to initialize the weights. And you're looking at the direction of the gradient, meaning all the partial derivatives with respect to W. Like, well, what is the greatest rate of change I can get by tweaking W on this my f function, okay? You have a way of f. F is your loss, again, your objective function, so on. And I said it's depending on the input and the W, because I think it is in general. So it's the best way to write this down. And how big your step you're going to take is the alpha parameter, the learning rate, the step size, whatnot. So here's what it looks like if you had a valley. So this is where the algorithm gets tricky. If you have a value where one dimension's impact is much important than the other, there are two variables. One of them gets you to a different direction. You'll be doing a bunch of oscillations to get to your objective function, the optimal location, sorry. Well, if you have a nice and smooth curve, this is really fast. And so that's the idea. Well, what's wrong with gradient descent? There's a bunch of things that people don't like and don't use in practice. One is computing all derivatives can be more expensive than you would like. And this thing gets stuck in local minimas often. And so this is a first order method. There are two ways to get away with not getting stuck in minimals. And they're actually on the completely opposite side. One of them is complicate your problem, use second derivatives, and see if I'm leading to an incorrect direction, or is there something that I can learn from the curvature information, but it's even more expensive, right? Instead, I'm going to dumb down myself and go to the opposite direction and say that, well, if my gradients were not exact, I would make a mistake and get out of this minima. Like if I have a sharp minima, and think of this as hill climbing versus simulated annealing, if you have seen this thing. Hill climbing will get stuck in a local minima, but if you allow it to do stupid mistakes sometimes, it will jump out of that hole that it dug itself. So stochastic gradient descent has these two advantages. One is cheaper. The other one is, since it's cheaper, it's not using all the correct gradients. It allows you to get out of these holes. It's funny. The algorithm looks awfully the same, except now you're going to assume that f, the general loss function, is, you can write it as a sum of little f's, where each one of them only depend on one sample. So f of I is just depending on x of I, the one piece of the sample. So instead of using the whole gradient, I'm going to be using the gradient with respect to only one x, right? So with one sample or example in my data. So pick one example from your data, take a gradient step based on the gradient with respect to that guy, and see what it's going to do. OK, sorry, I went ahead of myself. Well, that's great. The problem is, well, this is a very cheap computation, and this is very serial. Like, I take one sample at a time, right? So that looks problematic because there's not much performance to be gained in terms of vectorization. And second, there's not much to parallelize here. So instead, I'll take B samples. Like, it's not N, not 1, something in between, B. OK? So that's what the so-called mini-batch version of SGD. Important points. This is not a descent method. So the real optimization people will complain. But I think the debate is unfortunately settled in a non-academic way by popularity contest. So everyone understands SGD, so we'll stick to it. What I just said, performance and parallelism requires batch training. and larger batch sizes can hurt convergence for the same argument that I said for the gradient descent. Because the gradients are not perfect, they allow you to get out of local minima. And this is why it's not a descent method, because you're not using the correct gradient. You're just using gradient by looking at one example only. You might sometimes increase your error. But overall, you're going down. That's why it's not a descent method. Again, it's just a name. It doesn't matter. You can call it a descent method. Overall, it goes down. Here is one issue. OK, so training is performed with an optimization algorithm like SGD. But as you can see, there is a bunch of gradients here, right? SGD is relying on these gradients. So who computes these gradients? There needs to be a way to compute these gradients. And my neural network can be pretty deep. So I need the gradient at every level of the neural network. So the method to compute the gradients is called backpropagation. It doesn't matter how many books tell you that this is a training algorithm. Backpropagation is only an algorithm to compute gradients. The training algorithm is SGD. I think people are learning that too. The deep learning book finally says this correctly, the one that came out, Goodfellow and company. That might be the first machine learning book that actually doesn't call backpropagation as a training algorithm, because it's really repeated application of chain rule from calculus to find the derivatives with all the previous layers. And it's just a special case of a very well-studied problem. It's called algorithmic differentiation or automatic differentiation. Again, unfortunately, these people gave two different names to the same thing over the years. The deep learning community now understood that there is something called automatic differentiation and does a generalization of backpropagation, but they didn't figure out yet, maybe they will listen to this, is automatic differentiation and algorithmic differentiation are the same thing. There's a bunch of books on this. Unless it's your research, you don't need to learn these, but if you care, know that it's not special to deep learning, and there's machinery to do that. OK, let's come to parallelism. After a little bit of rant, here's the one way to parallelize this thing. So I need to, if I distribute my data to processors, like I have n examples, I'll say every processor gets a bunch of examples to train. But I will say that my neural network is not gigantic. I will replicate it in every node. Sometimes works. In general, this is the standard way of doing it. For some reason, I keep losing resolution on this photo, but whatever. So you keep some concept called a parameter server. All this is keeping is your gradient information. Whenever one of the processors get a new gradient update based on its local computation, it pushes it to the parameter server, so everyone can see it. Okay? And this is not a great design in terms of parallel computing. Not something we like to teach, because it's some sort of master process. It creates a lot of bottlenecks in terms of performance. So we'll see alternatives to get around this. But I want to say one more thing. How do you push the gradients to the parameter server is a big debate right now. Right? So one way is let everyone update whenever they have a new gradient, and that's called the asynchronous way. Or you can say that, well, I'll say everyone start local training, and next time we're going to synchronize before we use the next gradients. So everyone will wait before they push their gradient updates. So that's the synchronous way. There are advantages of both. You can probably think that asynchronous is going to be faster in case some processor goes slow. You might be right, but it has also its disadvantages. That it's not reproducible. If you have a bug, you'll be spending quite a bit of time to figure out, because every time you run, it's going to make a different order of updates. And sometimes it might hurt convergence, though people have figured out that there are ways to get around this, which basically means you have to use some concept called momentum, which is, again, an old concept. We're not going to get into that. That debate will settle itself unless you're working on that field. Shouldn't concern. If you're working in that field, it's an interesting problem to work on. How do you get around the master process parameter solver bottleneck? I'll give two ideas. For synchronous SGD, what it looks like the best way to do this is really instead of pushing it to a master process, just use good old MPI old reduce. So nobody is responsible for keeping this server concept. So after a certain number of time steps, everyone calls an all reduce and gets the new gradients. So there's no centralization. And if the network is optimized for this, pretty good. If you have an asynchronous SGD process, instead of pushing it again to a parameter server, you can do peer-to-peer gossiping. So you just basically propagate this information within the network using some sort of nearest neighbor information propagation. Again, the whole asynchronous SGD idea is that stale gradients are OK after a while. So this might actually make the staleness a bit more problematic, but it still converges in practice. There's a few results on this paper by Kurt's group. But I think one important connection I want to make is SGD is SGD is a matrix operation as well, right? A linear algebra operation. So what is this? It's every stage, what I'm doing is multiplying a matrix called W, which are the weights. Now look at the dimensions of this matrix, m by m. N is the number of outputs, m is the number of inputs. So it transforms the inputs to the outputs, right? And what are the inputs? Well, that is also m by b. I forgot an m here, but it's natural. I think you can see that. If I can do matrix multiply, this is m. And capital B is the batch size, the number of examples I picked for this stage. And that's essentially what's happening. Right? So this can be dense if you have a fully connected network. If you have a sparse neural network, this might be sparse. But the impact of parallelism is significant. What's happening? So W is not important. W is the model. In the data parallelism case, it's replicated. That's easy. But then when I do data parallelism, the batch size shrinks per processor. Like if I have chosen a batch size of 1,000 and I'm using 100 nodes, I can't make 1,000 times 100. That's too much of a batch size. I will lose convergence due to the reasons I explained, that now it doesn't look like stochastic gradient descent. It will look like the gradient descent. Right? So I have to keep the batch size to a theoretical maximum. And if I increase processors, the per processor batch size, the little b, shrinks. OK, this is not b over n. This is b over p. Another bug has been found. Well, what's the impact? The BLAS will have issues getting good performance if you have really skinny matrices. So that's one issue, right? So they're both getting smaller and skinny. So data parallelism might actually hurt your single node performance. Keep that in mind. So the alternative of data parallelism is, again, from an old paper by Google. Man, old is 5 years these days. Is, well, what if I distribute the model to processors? Like I partition my neural network to, in this example, 4 processors. And one interpretation of this is, again, what just said, you're partitioning the network. But for computational perspective, what is this doing is really, you're doing the matrix operations in distributed way. So matrices are distributed. Now W is distributed itself, the weight vector. And you're just doing the good old summa algorithms or whatnot. So the unfortunate reality is the matrices are not large enough to justify this yet. But I don't think anyone actually has tried the communication avoiding algorithms where small matrices scale very well because you have the replication ability, right? The 3D algorithms that we've seen from dense linear algebra. Here's a class project. And the last subject. This is good. It's actually not a major topic. Any questions on support vectors or neural networks? Good. Here's some unsupervised learning algorithm called non-negative matrix factorization. The word matrix factorization is overused, probably. In fact, in machine learning, especially given that it's not a factorization. Really, what you're trying to do is you're trying to find a low-rank decomposition of the matrix A, where, again, examples by features. You're trying to compress the feature dimension in general. Sometimes you can do the other dimension, too, but that's often what you're doing. You're trying to reduce the dimensionality of data points by shrinking its feature set. But instead, here you have a constraint. It's these little things that I put under the minimum sign. It's like W and H should both be non-negative. There shouldn't be any negative entries. Why? Well, this basically tells something. Let's say gene expression values. You're trying to factorize this thing. Well, gene expression runs from 0 to 1, let's say normalized, and you get a bunch of negative 71s. It doesn't make a ton of sense, right? The biologist doesn't like to see minus 71 for a gene expression value. So he wants to be able to make sense of the reduced dimension. So that's why there's an argument for interpretability, one argument. There is other arguments for that. But the issue also here is factorization is not a correct name because you're only approximating it in some norm. In this case, Frobenius norm is what I put there, but some people use a different norm. And keep in mind that NMF is not one algorithm. It's just no matter whatever factorizes your matrix or approximates your matrix as two components using non-negative components is an NMF algorithm. So there's a bunch of algorithms. Here's one framework that does that. The so-called alternating updates. I think this is a new name, but I like it, so I used it. So what do we do? Well, solving for two operations is quite ill-defined, right? So what I do, I initialize to one of the matrices to something. There are algorithms for good initializations, doesn't matter. And I'll fix that guy, and now I have only one unknown. Now, if I fix H, I know H. So I know H and I know A. So I need to solve for W. OK? And then now I found the W, use that W, and solve for H, and repeat. So fix one of them, solve for the other one. That's why it's called alternating updates. Many algorithms fall into this framework. The oldest algorithm on this probably is multiplicative update, and it actually falls to this framework. The second algorithm that became popular was alternating least squares. So in this manner, you were solving least squares. But that algorithm didn't care about the non-negativity. And then came the alternating non-negative least squares, meaning at every iteration, solve the exact problem, not just So what the alternating least squares was doing is was solving something, and it was getting negative entries, was brute force forcing them to be 0. But somehow it was converging to something meaningful. But of course, if you're more intelligent, you converge faster. So this is a general idea. I give you a representative of papers. It's not about a survey. It's just a good paper. Caveat emptor. It's not the only method for finding an NMF. Alternating updates is one framework. In fact, stochastic gradient descent can also find a NMF, non-negative matrix factorization. And here's a good paper there, too. But for the purposes of this class, this is actually going to be an implicit algorithm in terms of parallelization, meaning we're parallelizing individual linear algebra operations. So what is the main computation in here? It's the large-scale matrix multiplies. In order to update W given a fixed H, you want to do 2 matrix multiplies. HH transpose is kind of easy because they're tall, skinny. But AH transpose is large because A is your whole data matrix. And similarly, you have to do it. This is definitely wrong. A transpose W is what it needs to be. Bug number 3. But it's gigantic matrix multiplies. So some facts, in general, W and H, which are the factor matrices, are dense. But they can be sometimes sparse if the output really needs to be sparse. Just like the non-negativity increases interpretability, there are cases where the scientist might want the output to be sparse or even have a particular structure. Like in the output, he might say that, look, I'm modeling this room, and there is a door there, meaning that there has to be a 0 there. Okay, so, but often it's not just that exact. It's more like you enforce it by some penalty so that you get more sparse output. So in general, they're dense, but there are cases where one of them can be sparse. A is often sparse because many applications have sparse data, but sometimes can be dense depending on the application. Just to get you an idea about the skew of these problems, this is what it looks like, right? Because this is a low rank approximation, the W and H matrices are tall, skinny, and short, fat, respectively. But A is not that skewed. So what's the algorithm that does this? Well, you need to parallelize these operations. And really, what these guys have published, Cannon, Ballard, and Park, is choose the best algorithm for matrix multiply depending on the relative sizes of the dimensions of the matrices and the number of processes you have. That's all there is. There's no new algorithm, but we know all the best algorithms. So pick the best algorithm depending on which matrix multiply you're performing. And it's beautiful. So there's one assumption in this paper is it never communicates A, the data matrix, because the assumption there is the rank you're approximating is so small that W and H are asymptotically smaller than A. So there is never an advantage of communicating A. Is that true? That's another class project if you care about it. Here's the work a grad student, Pamporn, did, and I was a co-author, where we didn't look at NMF in particular. We said, what is the space of sparse matrix times dense matrix? And you have to understand that I said, like, A is usually sparse, and W and H are dense, right? So this is exactly the problem. And we studied, like, 6 different variants, 3 different one-dimensional algorithms, 2 different 2D algorithms, and so on, and plotted the areas where they perform best. And it looks like there is an area where a different algorithm shines. This is 3 different plots because one of them starts with a almost square A, one of them starts with a tall A, one of them starts with a fat A. It's not in this paper, but photo, but for different A shapes, it shows which algorithm will perform best. And there's regions here. You see there's 1.5D algorithm is like a 1D algorithm, except with some replication. And 3D summa is what you've seen, communication avoiding summa, applied to the summa, sparse case. And so the point here is for every skewness, there is a part where a different algorithm is better. And all the 3D algorithms actually communicate the data matrix, a sparse matrix. So there is a place for them. It just depends how much you want to push this, right? In order to be here, you have to push your number of processes to pretty high numbers. Or your matrices should get close in terms of non-zeros. If your matrices are very different, one of them has very fewer non-zeros than the other, and you have low processors, it is indeed correct that you're never going to move A. Why? Because A is bigger, right? So, but the juries might be still out. A bunch of things I didn't cover today. Sparse inverse covariance matrix estimation, mouthful. It's really estimating partial correlations in the data, right? When I regress out all the effects of all the other samples in this data, what is the inherent correlation between point sample A and sample B? That's what it estimates. And that was the driver of our work on sparse times dense, because that's the inherent problem. Lots of clustering algorithms are very parallelizable. A very famous algorithm from bioinformatics, Markov cluster, does sparse matrix times sparse matrix, and then does the selection problem we've seen in an iterative way. Spectral clustering is really about eigenvalue and eigenvector computations. So this is also ends up being SPMVs in some sense. K-means clustering, as I explained with respect to an earlier question, parallelizing it in the most efficient way requires hierarchical data structures, but we'll see similar things later. We already seen some. For that on, I'm actually right on time and even earlier, 2 minutes. So I'll let Aditya take over. Questions? Hopefully this was helpful. I'll fix the bugs before I post them. Oh my God. Oops. Oops. Microphone.
You're right, we're right.
No, no.
No?
The reason is you always look at the screen.
Oh, that's
So you
fair.
turn your head towards the screen.
All right. Can you hear me in the back? Good? Perfect. All right, so can't see the slides, so that'll be good. If you could. All right, perfect. So hi, my name is Aditya. It's kind of strange being on this side of the room, actually. So I'm a graduate student working with Jim Demmel and Michael Mahoney, and I'm going to go a little deeper into some of these machine learning algorithms and how we should try and parallelize these. So this goes back to the asynchronous versus synchronous algorithms and implicit versus explicit parallelism. And we'll sort of look at the trade-offs between all of those. And so as Aiden was saying, a lot of these algorithms are communication dominated. So we really want to try and avoid those, especially for large scale computations. And this is sort of one way you could try and get to that goal. OK, so let me kind of start off with reminding you about where machine learning sort of starts in terms of application areas. And then we'll sort of look at the optimization algorithms. And then we'll do a deep dive into block coordinate descent. And then show how you can kind of rederive this algorithm in a different form and get a communication avoiding variant. And of course, it's not just enough to show that this is the case in theory. We got to show that it's scalable in practice. So there's some results on that. OK, so I'm going to talk about the applications. So this is a non-exhaustive list. I mean, machine learning is basically everywhere. So let me start off by just categorizing it into 3 different parts. So one of them is going to be regression problems. So that's, and simply you can kind of think of that as doing line fitting. So if I have a cloud of data, I want to draw a line through it and get some sort of prediction. So that's kind of one way you can do it. And that sort of appears in biology and econ and business. So I know 267 is kind of a diverse crowd. So you probably have applications that you've used regression on. OK, so the next class is sort of binary classification or multi-class classification. So if you look at binary classification, you can sort of look at spam filters as one example. So you have a bunch of email in your account. You kind of want to have the spam filters say it's spam or not spam. Oftentimes that's an optimization problem. And I don't know about you, but my spam filter often gets it wrong. But it is what it is. And then there are multi-class classifications. So those are sort of more difficult problems. So one example is all right, I have a whole bunch of people, and they're writing numbers and digits and stuff. And I want to recognize the characters, right? So that's a 10-class problem because I have digits 0 to 9. And so it's going to be a hard optimization problem because my chicken scratch is going to be very difficult to kind of compare against all of yours. OK, so and then you can also do clustering. So I didn't mention that at the very last part, and they're actually really cool problems. So you see this a lot in sort of disease and viral propagation stuff, which is very social and networky. So you kind of look at how that propagates through the through sort of the general population. You have recommender systems, which is like Netflix and trying to recommend shows that are similar to The Walking Dead, because I binge on that. And social networks, so this is Facebook trying to figure out who the popular people are or who the celebrities are in your friends list. OK, so that's kind of the overview. Let's do a deeper dive into the optimization problem, and we're just going to do linear regression. So this is sort of the simplest problem you could possibly do. It may not work for your data, or you may not want to use it, but it's one example. So it goes by another name, and it's least squares. So you may have heard the alternative name, but you can write this in sort of as a minimization problem. So you have this data matrix X that's going to have some features, and I'm going to label that D, and it's going to have some number of samples, N, right? And then I'm going to give you a bunch of labels for each one of these samples, and that's going to be my vector Y over there, and that's going to be of dimension N. And so what I want to do is find a set of weights, and this is a d-dimensional vector here, for all of the features of my data matrix that will closely match my labels Y. So this is sort of a prediction problem. So you can go ahead and put your calculus hats on and go ahead and do some number crunching here. And so if you solve this, you'll get a closed form solution that is basically going to be what's called the normal equation, right? So you just have this x times x transpose. That's a Gram matrix. It's going to be of d dimensions. You invert that, and then you multiply by x times y. So that's kind of just a standard way of solving it. Now, would you really want to do that? No. I mean, there's actually two reasons for not doing this. One is this is numerically unstable, so you kind of want to do some sort of factorization, really. But another reason is you're doing matrix operations on the entire data matrix, right? Because the Gram matrix on the inside of those parentheses is going to be expensive to compute because you're doing a d squared n operation, right? Because it's a d by n matrix, multiplying it is going to be expensive. We want to avoid that. And so block coordinate descent is actually a way to avoid that computation. So the idea here is that, well, I don't want to do the entire matrix computation. I want to just subsample, right? What would happen if I did that? So I'm going to pick a block size b that's going to be less than d, of course, greater than or equal to 1. And then I'm going to just solve that local subproblem. And when I do that local subproblem, the flops are going to be much cheaper now, right? It's just going to scale as b squared n, which is less than the old algorithm. But I only get a solution for the subsampled rows of the matrix, or the subsampled elements of the w vector. So I need to fill in the rest of them. So this is an iterative algorithm now. And so that should set off alarm bells because iterative means communication in the parallel case. So we want to try to minimize that, right? OK, so let's look at the parallel computations, though, just to kind of drill home the computational phase. So recall that we're going to compute this b by n matrix-matrix product. So if I take my matrix x tilde and I partition it in a 1D column layout, so each one of the processors gets 1/p of the columns, right? So when you do that, x tilde times x tilde transpose, all of those are local problems, right? Because I can just compute. So P1 here can compute this block times this block without having to communicate. And then all the way up to processor P that can multiply this block times this block locally, right? But then those are all sort of partial matrices that you need to now add up. And so the way you would add it up is just by calling MPI all reduce. Now that's an expensive step, right? Because you need to have all of your processors communicate. And so that's expensive. And on the side, you also need to compute x tilde times y. Again, that's kind of simple because it's just a vector. So that's going to be a cheaper computation than the matrix multiply. And when you're communicating it, well, just pack all of these messages together, right? So when you communicate the Gram matrix, communicate that vector as well. OK, so there are a couple of assumptions when we do this operation, right? One is that when I do the MPI all reduce, each processor has a copy of that b by b Gram matrix. So that means I can do redundant computations on all processors. And that's kind of nice because that part requires no communication. And it also implies that I replicate the solution vector w. So they're going to be kind of synchronized on all processors. Now, if they're replicated, then each processor can update w locally. They don't have to communicate that, and everything's kind of nice. But this communications phase is going to be expensive, right? OK, but how can we fix that? Well, so one of the interesting things with the block coordinate descent algorithm, because it's so iterative, is that you have these sort of recurrences that you get, because at every iteration, you're going to compute this b by n matrix multiply. You're going to update the w vector. You're going to select a new set of b rows, and you're going to keep doing it again and again and again. And that's a recurrence. And so what you can do is try and unroll that recurrence, sort of algebraically. So you write down the problem, you derive a few steps, and unroll these recurrences. And I'm going to let s, so that's going to be a variable I'm going to introduce, and that's going to represent the amount that we unroll. And so conceptually, at least, what the difference between the block coordinate descent and the communication avoiding version is that you just pick larger blocks, right? So rather than picking b blocks here, you're going to pick s times b blocks. And Now, that means that I now compute S squared more flops, right? Because matrix multiply here scales as S squared B squared times N. So that's an S squared factor more flops. And you also get a much larger Gram matrix. So you increase the message size of your MPI all reduce. But it's also, so the one difference is that rather than so what is the difference between, say, selecting B equal to S times B, right? So why can't I just choose B to be really large? And the reason for that is when you do the inversion, right? When I compute this inverse here, that's a cubic operation. So the original algorithm is going to do B cubed flops. And if I were to just arbitrarily pick a larger dimension or a larger block size, I'm going to take this inverse to be B cubed, right? Or S cubed, B cubed. So we want to avoid that. And so what that implies is that we need to have a clever way of combining the Gram matrix that we get. OK, so let me pause really quick for questions. All right, cool. OK, so when I compute this Gram matrix, so you have this giant S times B by S times B Gram matrix. And we only want to spend B cubed operations on the inverses. So I'm going to start partitioning the Gram matrix. And so what that's going to look like is way on the top left, that B by B block over there, I'm just going to invert that and compute delta W1. So delta W1 is the solution for that B subproblem, right? And now I have a whole bunch of other stuff left over in the Gram matrix. And what I'm going to do is pick this off-diagonal block here and multiply delta W times that, or the other way around. So it's going to be this block times the delta W1 that you get. And the reason you do that is actually the off-diagonal block here is just a projection matrix, right? So what you do is you take the solution that you get from this first block over here, and you take that matrix vector product, and that takes the solution and projects it into solution space of delta W2, right? And that's a cheap operation. So that's just a B squared operation to compute this. And then once I have that residual update, I can just compute delta W2 using a linear combination of this guy and the solution delta W1. And so, I mean, the algebra is sort of a little hairy to get to this space, but that's basically what you're doing. You're kind of using the block diagonals as your matrices that you invert, and everything else that's on the off diagonals are going to be projections from all the previous solutions. So if I were to, so this is an example with 2 by 2. If I had a 4 by 4 matrix, then rather than having just one block off diagonal, I'm going to have a whole bunch of block off diagonals, and I'm going to multiply those by delta W1, delta W2, and so on and so forth, all the way up to the step that I'm currently on. And so if you just kind of compare this to the old block coordinate descent algorithm, the difference there is that the communication avoiding one gives you 2 solutions with the price of 1 MPI all reduce, right? You've only done the MPI all reduce once on that bigger Gram matrix, but you get 2 solutions. And so in general, what that means is that since S is a tuning parameter, I can get S vector updates, S solution updates, for every 1 solution update that block coordinate descent does, right? So in terms of the number of all reduces that I need, it's more efficient, right? So since the algorithm is iterative, if I require 100 iterations to converge, then block coordinate descent is going to require 100 MPI all reduces. The CA version is going to require 100 divided by S, right? So it's slightly more efficient in that respect. OK, so that is kind of a difficult slide to parse, I think. So let me pause again for questions.
Yeah, so where are the delta W's defined? Like, what is that?
So the delta W's are going to be the solutions that you compute at each iteration.
Oh, okay.
And so those are just the B-dimensional solutions because you're going to pick a subset of B features off of all the features that you have, and you're going to update only those. And the rest of them in the solution vector are going to remain fixed because I haven't touched them. And so since I haven't touched them, in the next iteration, I'm going to pick a new set of blocks, and that's going to give me a new subproblem solution. And so you just keep doing that. And all of these delta W's are going to be the solutions for the blocks that you picked. Yeah.
So this only used everything at the bottom left part of the matrix, and that's because it's symmetric?
That's right. Yeah, so the Gram matrix, just because you're computing x times x transpose is going to be symmetric. So really, you only need to look at the lower or the upper triangular part. And so that's actually a nice way to avoid communicating a large matrix, right? So rather than doing a communication with the entire Gram matrix, I can just divide that message size in half because it's symmetric. Right? Yeah, so that was good. That's a good optimization that you can make in practice. OK, any other questions? All right, we'll get to some results now. So let's go ahead and implement this in MPI. I'm sure you had a lot of fun with your particle methods and probably familiar with MPI by now. So I'm going to implement it in CNMPI, and I'm going to run it on NERSC Edison. And I'm going to set it so that I'm using one MPI process per processor. So that basically means that for each node of Edison, I'm going to run with 24 MPI processes because it's got 24 cores. And now in the slides, I kind of implied that the data matrix is dense. Well, really in practice, it's sparse. So I'm going to store all these matrices in sort of a compressed sparse format. And so it's OK if you're not familiar with that. You're going to get to it in the sparse linear algebra lecture later on, but just sort of a heads up about that. And so we're going to run this on a bunch of machine learning data sets, and they're going to be small scale and large scale and different sparsities. And what I'm going to do is plot the strong scaling results. And by strong scaling, what I mean here is if my algorithm takes 2 seconds on one processor, then it should take 1 second on 2 processors. Right? So every time I throw more processors at the problem, I'm hoping that the running time gets faster. Right? So what I'm going to plot here is the original block coordinate descent algorithm. That's going to be in these dotted lines. And then the solid lines are going to be the communication avoiding method. And all the different markers are the different data sets. And then I'm also going to plot the ideal scaling lines for each one of these data sets. So again, by ideal scaling, I just mean if I double the processors, I should get half the running time. Right? So it should be a 2x speed up. OK, so if you were to plot this for a block size b equals 1, so at every iteration, I just choose one feature at a time to optimize. And if I were to do that, that's a huge critical path, right? I mean, so this goes back to what Aiden was saying. If you do one feature at a time, you're increasing the critical path of the algorithm. It's going to be more expensive in terms of communication. And that's where the communication avoiding method really works. So in all of these cases, I'm going to set S to be something that's optimal. So I run it for a whole bunch of values and pick the best running time out of those. And so if I were to do that, I get somewhere between 3 to 4.8 times faster than the old algorithm. And just keep in mind that this communication avoiding algorithm doesn't change the numerical behavior of the old algorithm, at least in exact arithmetic. So what that means is that the convergence rates and the sequence of iterates that you get are exactly the same as the block coordinate algorithm. So you're going to match it exactly in solution accuracy. OK, so what if I increase the block size to b equals 8? So when I increase the block size, I increase the floating point operations that I need to do for the subproblem, because I now have to compute a larger matrix-matrix multiply. And I also increase the message sizes so that so actually calling the MPI all reduce is not the only bottleneck. It's actually the message size as well. So when that's the case, what we're going to get is slightly less speed up, so more modest speed ups because you're now more flops and bandwidth bound and not latency bound. And so you're only going to get 1.4 to 1.7x speed ups. OK, so let's dive in a little more and look at the running time breakdown. And so now I'm just going to fix the number of nodes to be 1K. And on the left, I'm going to plot block size b equals 1. And on the right, b equals 8. And I'm going to show you the running times for computing the Gram matrix, which is doing the parallel matrix multiply. And then the gray part is doing the actual subproblem solution. So that's going to be computing the inverse of that ground matrix. And you can't really see it. That's because it's such a cheap operation. Is like right in the middle over there. And then all the white bars are going to be communication. So this is kind of pointing out that when b equals 1, my critical path is really long. And there's lots of communications. So communication dominates here. And so as we kind of claimed with the communication avoiding algorithm, as you increase this factor s to be really large, you're going to decrease the amount you communicate, right? Because you reduce the number of times you do the MPI all reduce. And you get a factor of s vector updates. But there's also a nice weird consequence, which is that you get some scaling in terms of flops as well, which is kind of strange, actually. And I'm curious if any of you could point out why that is. All right, so this actually goes back to what Aiden was saying, which is that BLAS routines in general are very bad at, or I shouldn't say they're very bad, but they're not going to be optimal on really small, thin matrices, right? When the block size b equals 1, it's just a single vector, right? You're doing a dot product. And doing a dot product is memory bound, right? Your processor is literally just waiting for your DRAM to serve you the data. But when s equals 32, you're not computing a 32 by 32 matrix multiply. So this goes back to assignment 1 now, when you did all of the blocking and stuff like that for matrix multiply, exactly the same story here. So because you're blocking everything, you're going to make the flops go much faster too. And so for block size b equals 8, the story kind of inverts itself. So the flops are going to be much more expensive because I have a larger block size, and communication is not as dominant. And so there, even though the communication avoiding algorithm decreases communication, it increases flops, right? Because I have to compute this much larger ground matrix. So there is a sweet spot right around here, but after that, it kind of tails off. And so the sweet spot here, again, the reason the flops scale is for the same reason as with the b equals 1 case, because your local floating point operations are running much faster and more efficiently. OK, and let's kind of finish things off with a giant heat map of all the speedups that you can get with the communication avoiding method. So on the x-axis, I'm going to compare the original standard algorithm way on the left here. And then the communication avoiding one with s for various values. And the y-axis is going to be the block sizes. And on the left, I'm going to plot what happens at small scale when you have only 64 nodes. And on the right, when you have 1,000 nodes. So the idea here is, 64 processors communicating is much cheaper than 1,000 processors communicating. So what we should expect with the CA algorithm is that when you increase the number of nodes and when you're more latency bound, meaning b is really small, you get huge speedups. So in this case, you're getting only 1.8x at small scale, but 4.1x way over here. And in the small scale, when it's only 64 processors, you get a modest 1.1x, so basically no speed up. And then here, you're going to get 1.38x faster. OK, so let me quickly summarize stuff. So the CA method, if you know that latency is the dominant term, meaning just the act of calling the MPI all reduce is the expensive piece, then these algorithms, then the new version kind of does better. And it does better without sacrificing convergence rate. And the nice thing is the idea is fairly general. So this actually comes under an umbrella of algorithms called S-step methods. Again, you'll get to that in the sparse linear algebra lecture, I think. And so it kind of extends to a lot of machine learning problems. So you can do lasso and all these different types of regularized least squares. It also works for kernelized ridge problems. And we're kind of working on extending it to like SVMs and logistic regression and deep learning. So lots of interesting projects there. So this is something I didn't mention during the lecture, but this is also more general than just the block coordinate descent method, right? Because all I did was kind of unroll some residuals and recurrences and stuff. I can do the same thing for stochastic gradient descent and all of the different flavors of algorithms because the communication avoiding method is really dependent on the minimization problem you want to solve. So for example, lasso versus ridge and all of those problems. So it really depends on properties of those and not the algorithm. So you can avoid communication in SGD, so there's an interesting problem there. So, all right, let me end with that. Right on time.
The previous slide, what was the computer there?
This was Edison.
So the theory that Edison is one of the lowest latency networks.
Yeah.
So you should get better speed ups on cloud, right?
Mm-hmm. Absolutely. So that is an open project if you're interested. If you want to run these on, say, Spark or re-implement it in like a MapReduce framework and test it out in the cloud or on Edison, that's also a good project for
Just MPI on cloud should give you better.
yeah, that too. So MPI on cloud. So you could also do that. All right, any other questions? All right, wonderful. Thank you.
You don't get clapping.
Yeah, exactly.